Hello and welcome to today's lesson. Before we start, for this lesson you will need a pen, a ruler, a calculator, some paper or an exercise book, and no mobile phone unless you're using this to view the video on. Best off, remove any distractions. If you need to pause the video to go get the equipment, then please do so now. In today's lesson we're going to continue with our investigation into electromagnets, and today we're going to focus on collecting and presenting data. We are still looking at our topic on how do magnetic fields produce electricity, but today's lesson we're going to focus on the question, how do we collect and present data? So before we start today's lesson, let's just see if we can remember from last lesson what the word reproducible means. 30 seconds to write down a definition. So, reproducible means two or more different people can repeat an experiment and produce similar results. And if you remember from last lesson, we were looking at the hypothesis that increasing the number of coils wrapped around an iron core increases the strength of an electromagnet. And we wrote a method for that. We're now going to watch a short video where Mr. Watson will show us how to set up the equipment.
Hi everybody, I'm Mr. Watson. I'm the Head of Science at Outwood Academy Freeston, and I'm going to show you an experiment today where we're going to investigate a factor that will affect the strength of an electromagnet. Just a reminder of what an electromagnet is. It is a temporary magnet that is created when an electrical current is passed through a coiled wire around an iron core. There are three factors that will affect the strength of an electromagnet. We've got the size of the electrical current, we've got the iron core itself, but the factor we're going to look at today are the number of turns that are placed on the wire that is coiled around it. So that will be our independent variable today, will be the number of turns on the coil. In order to do this experiment, I'm going to need a way of measuring the strength of the electromagnet, and to do that I'm going to see how many magnetic iron paper clips we are able to pick up with it, and obviously the stronger the magnet, the more paper clips we'll be able to lift. So that will be my my dependent variable will be the number of paper clips lifted. We are going to need some control variables in order to make sure we get valid results. And in order to do that, I'm going to need to keep the iron core the same throughout. I'm going to use the same iron core. I'm going to keep the voltage from my power pack the same as well. We're going to use 8 volts for that.
Okay then, before we watch the next video where Mr. Watson will do the experiment, I'd like you to copy down the table below so that as we watch the video you will be able to fill in your results. I'm going to give you 1 minute to do that. Okay then, let's have a look a video with Mr. Watson carrying out the experiment.
I'm going to begin just by proving to you that this isn't magnetic to start with, and in fact you can include this in your results as a control, because at the moment I've got the iron core, but of course with 0 turns of the wire around it, because there isn't a wire around it, and I just want to see this should pick up no paper clips because it isn't magnetic. So you can include that as your first result. With 0 turns, we have 0 paper clips lifted. I'm now going to make my electromagnet, and I'm going to go up in increments of 5 turns. So to begin with, I have got my iron core with 5 turns of the wire coil around it. I'll turn my power on, and as the current begins to flow, it creates a temporary magnet which will pick up, strong enough to pick up 1 paper clip. So with 5 turns, we lifted 1 paper clip. I'm now going to increase that to 10 turns. I'm still, as you can see, using the same iron core, and I'm going to keep the electrical current exactly the same. So they are some of my control variables. This time, with 10 turns, we have lifted, you can see that the magnet's stronger. This time it has lifted 4 paper clips. And now increase it by another 5 turns. So we now have 15 turns in total. Iron core's the same, electrical current's the same. And this time the electromagnet is even stronger still. So we have got 1, 2, 3, 4, 5, 6, 7, 8 paper clips lifted. And one final one with 20 coils around the core. Turn this on. Look at that. And that has lifted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 paper clips. And now you can process those results.
Did you get the results then? So Mr. Watson did the first set of results, and then he carried on and he repeated the experiment 3 times. So in this table I have then filled in for you the results for the second attempt and the third attempt. This will enable us to be able to calculate a mean. So that's one of the things that we do to ensure that our experiment is reliable, and it helps us to spot any anomalous results. So in the first row, 0, 0 and 0, the mean of that is 0. And at 5 coils, we got 1 for every one of the attempts. So again, our mean is 1. However, for 10 coils, when he did it 3 times, the first time he got 4, then he got 5, and then he got 3. So for this one, we need to calculate a mean. And the way that we do that is we add up the 3 values and then we divide it by the number of values. So that's 3. So it's 4 plus 5 plus 3 divided by 3. And that would give us an answer of 4. I'd now give you a minute to complete the rest of that table. Okay, so these are the results that you should have in your table. Now, often when we have a set of results, we like to present our results as a graph, and there's different types of graphs that we can draw. So first of all, you should look at your data and see which is the best type of graph to draw. So you can plot your independent variable on the x-axis, and in this experiment the independent variable was the number of coils of wire. We then plot our dependent variable on the y-axis, and in this experiment the dependent variable was the number of paper clips. Now, if both of your values are continuous, that means they are numbers, you should plot a scatter or a line graph like the one shown at the bottom. If one of your variables is continuous and the other is categoric, so a categoric variable is something that is absolutely definitely like hair colour or your favourite football team or a type of animal, then you should plot a bar chart. So for this experiment we are going to plot a scatter graph. Now I'm going to go through how we would plot the graph for this experiment.
When drawing a graph, we always make sure that we have our independent variable on the bottom and our dependent variable on the y-axis. Now, other things to remember, it's always important to remember to use a ruler when drawing the axes for your graph, and I would usually always do them in pencil. However, because my graph paper is black and white, to make it stand out to you a bit more, I'm going to use a coloured pen. Now, we always need to make sure that we use as much of the graph paper as possible. We don't want a tiny little graph just up in the corner. So as a rule of thumb, we tend to use at least half the graph paper. Now my independent variable this time is the number of coils on the electromagnet. Now I'm quite fortunate in that this doesn't have a unit, so I don't need to remember to put the units, but if it did have a unit we must always remember to put that as well. Now I'm going from 0 to 20, so I want to try and space out 0 to 20 as much as I can on this line. So if I start here at 0 and every two big squares I go up 5, then you can see that I've nicely filled that part of the piece of paper, and I can draw my line like so. Now my y-axis needs to go from 0 to 16. So if I look this time, then it could be that if I went up in ones, let's have a look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I'm going to run out, so I'm not going to get to 16. So let's go back and look and see if we can do it in 2s. 2, 4, 6, 8, 10, 12, 14, 16. And that's going to give me a nice axis on my graph, so I'm going to do that. And if I go 2, 4, 6, 8, 10, 12, 14, 16, and if you remember, this was the dependent variable, was the number of paper clips. And again, this doesn't have any units, so I don't need to put any units on that. You'll notice that on both axes, although the scaling is slightly different, there is still an equal number of squares between each on the axis. So for example, on the x-axis going from 0 to 5, and then 5 to 10, and then 10 to 15, and so on. In each case there are 10 small squares between them, so I've got exactly the same number between. And then going up here I've got 5 small squares between each of my values on my axes. It's important that when we're drawing axes that we keep those equal. If I then look at plotting my values, then at 0, when there were no coils, it didn't pick up anything. Just put a nice neat cross. At 5, it picked up 1. Now 1 will be halfway between 0 and 2. And if you notice, each time I'm just using a really simple cross. No big coloured in circles because that makes it less accurate. So if you were drawing this with a pencil, nice sharp pencil and a nice fine cross. At 10 we collected 4. At 15 we collected 8, and at 20 we collected 16. So the next thing we need to do is connect our points, and looking at this, if I took my ruler, this isn't a straight line. In this case we have got a curve, and sometimes the line of best fit in science will be a curve. That's fine. What we need to do, and it's alright, you can turn your graph paper around. I like to go from left to right because I'm right-handed. We do not draw a dot to dot. It needs to be a smooth curve. If I just take this, and with a curve, these look like they pretty much all fit on the line of best fit. Could have probably done that one there a little bit better and gone through that. So that is a graph of our results.
Okay, so key things to remember are success criteria when we draw a graph. We must always label the axes, and if the values have units, we must include the units. We have to use a consistent scale. That means we have to have the same number of squares between each of our numbers. They could be different on each axis, but on one axis they must be the same. It's really worth taking time to plot points correctly and go back and double check, because that's easy marks lost. And when we're plotting points, a nice neat cross with a sharp pencil. We then draw a line of best fit, and that could be a straight line, or in our case it was a smooth curve. And then finally we describe the relationship, in this case between the number of coils and the number of paper clips attracted. Okay, then I'd now like you to write a conclusion for our experiment. What does the graph tell you? Now, when writing a conclusion, remember to use the axes labels. So starting with the x-axis, what happened as you increased the x-axis? So in this case, I'd say, as I increased the number of coils. You then need to comment on what happens to your dependent variable on the y-axis. Does it increase or decrease? Then you need to improve your answer by quoting at least 2 sets of data from your graph. So I might write when the number of coils was 5, the number of paper clips was 1, and then when the number of coils was, and pick another one and compare it. And then finally, comment on the shape of your graph. Is it a smooth curve? Is it a straight line? Does it increase? Does it decrease? Does it go through the origin? Okay, I'm going to give you 3 minutes to do that. Let's have a look at a model answer then. So the first thing I would write was, as the number of coils increases, then the number of paper clips attracted to the electromagnet also increases. I'd then say at 5 coils of wire only 1 paperclip was attracted, whereas at 20 coils of wire 16 were attracted. So I've proved the relationship. And then finally I'd say the relationship was a curve with a positive gradient and that it started at 0, 0. Okay then, just to finish off today, have a look at the 2 graphs below and what is wrong with each of the graphs. I'm going to give you 1 minute to have a look at that. Okay, so did you spot it then? So on the bar chart, apart from the fact that the colouring's a little bit messy, they'd also forgot to label the y-axis. So we know it's the number of coils, but we've no idea what that relationship is. And then on the one on the right hand side, it's almost like a dot to dot. I would say this one, instead of being a curve like ours was, it's more of a straight line. And then the other thing that they've done incorrectly is if you look at their y-axes, then they have not equally spaced them out, have they? So they've gone from 0 to 4, and that's taken 5 little squares, and then they've gone from 4 to 7, which is an increase of 3, and they've given that 6, and then they've gone from 7 to 10, which is 3 again, but this time they've gone 4. So you can see that it's not a consistent scale, so that would also be a problem. Right, that's it for today. See you next time.